Hello, Physics Nation. My name is Nate Larmond, and I would like to analyze this truss. We have a pin joint on the left-hand side. We can produce reaction forces in the horizontal and the vertical direction. The roller joint over here can only produce a vertical reaction force. We have a symmetrical truss, but an asymmetric loading. So we have negative 1,000 pounds here, negative 250 pounds, and negative 500 pounds of force. So the first thing they're asking us to do is to define the free body diagram. That is what forces are acting on this thing. And like I said, it's only connected to the ground in two spots. So the center of gravity is not in the middle. I don't know. It's unclear where the center of gravity would be given these loading situations. But we're going to define the geometry, that is how long each one of these members are, and the angles in order to find the forces. So the physical geometry also defines the force vector geometry. The forces have to be in the direction of the beam. That's why the physical geometry is the same as the force geometry. Anyway, all we really need is Pythagorean theorem and the three trig functions here. And let's go over to my hand-drawn notes. So here's Pythagorean theorem. I started on the left-hand side. It doesn't really matter where you start. If you do, the key is to drop a plumb line, drop a vertical from the top, that is point D, down to the base of this left-hand triangle. Once you do that, well, we got a little right triangle on the left and a little right triangle on the right. And trig functions and Pythagorean theorem are a classic geometric way to analyze right triangles. So grind through the Pythagorean theorem, you get 4.24 for this left right triangle, and grind through the Pythagorean theorem. Now it's 2 squared plus 3 squared equals hypotenuse squared. That ends up being the square root of 13, or 3.61. And here comes the trig. I wanted to find this angle, but if the adjacent leg is the same as the opposite leg, that is if the slope is 3 divided by 3, or 1, then it's 45 degrees. It's right in between 0 and 90. But I just did the trig for fun. So sine of theta equals 3 divided by 4.24. That is opposite divided by hypotenuse. That's root 2 over 2 in math land. We like to say 0.707 in engineering land. Anyway, how do you undo sine? Well, you take the inverse sine of 0.707, and that returns 45 degrees. But like I said, that's really an intuitive solution. I didn't need to do the trig there. Over here, though, I did need to do the trig because opposite is 3 and adjacent is 2. Oh, okay, looks like I didn't do tangent. Looks like I did adjacent is 2 and hypotenuse is 3.61. So adjacent divided by hypotenuse becomes 2 divided by 3.61. Inverse cosine of 0.554 becomes 56.3 degrees. These guys are alternate interior angles. So 56.3 degrees here, that is angle ABD, is the same as 56.3 degrees here, angle BDE. You can find the complement of this angle right here. So 90 minus 56.3 is 33.7 up here. The sum of 45 and 33.7 is 78.7. That's this top angle. And I think the geometry is fully cooked then because of the symmetry. Oh, I guess in order to find this one, we're going to find the supplement of these two guys. So 56.3 plus 56.3 plus mystery angle, we don't know, equals 180. So that's how I found this angle right here. And after you fully define the geometry, all the lengths and all the angles, then it's a torque balance. So this thing is in static equilibrium. That is, the sum of all torques, or moments, is 0, and the sum of all forces in both the horizontal and the vertical direction are 0. This system isn't accelerating. That's why it's called a statics problem, because the bridge just sits there. And that's where we're going next. Pardon the scrolling. We're going to find the torque exerted about point A, about this pin joint on the left-hand side, by each one of these three forces. All right, so we have 1,000 pounds acting 3 feet from the pivot. That's R1. Then we have 250 pounds acting 5 feet from the pivot. That's R2. Then we have 500 pounds acting 7 feet from the pivot. That's R3. And because all of these forces are perpendicular to each one of these lever arms, we don't have to worry about FR sine of theta, because sine of 90 degrees is 1. So we just multiply the force by the lever arm. So 1,000 multiplied by 3 gets us 3,000 foot-pounds. The negative is because all of these rotations are clockwise. And the math teachers always say those are negative z rotations. Curl your right-hand fingers in the direction of the rotation, and your thumb points away from you or into the page. It's a negative z rotation. Anyway, all of these 3 torques are negative z, or clockwise rotations. We've got 250 pounds acting 5 feet from the fulcrum. That's negative 1,250 foot-pounds of torque. And the third one, 500 pounds of force multiplied by 7 feet of lever arm, is negative 3,500 foot-pounds of torque. And we didn't get to it in class, but we're going to figure out this mystery torque. We know the distance, and so if you know what torque has to counteract the 3 twisting loads, the 3 moments, the 3 torques, you can figure out what torque is required that's provided by this reaction force. And how wide is the entire structure? 10 feet wide. So like I said, we didn't get to that in class, but we're going to find this last torque. It's going to be equal and opposite to these 3 torques, and we can find the reaction force, the upwards force provided by this roller joint. But that's for the next episode. Thanks for watching.